discharge, and state of charge. Those are our main topics today, but I'm going to start with an overview. So SimpliPhi Power got started as OES Energy, as optimized energy storage, way back in 2010. And I know from a battery standpoint that from a general company standpoint, that might not seem like a long time, but from the rapidly evolving home battery storage and lithium battery market, that's a significant amount of history. So we have 12 years of history making lithium iron phosphate batteries, and we do that at our facility here in Oxnard, California. So we started out as a company manufacturing energy solutions, mobile energy solutions for the film industry, film and broadcasting. So you can imagine challenging environments such as maybe doing filming at the beach or broadcasting from a disaster zone where you could have potentially rough environmental considerations like hurricanes, that kind of thing. So we really developed a lot of intellectual property and worked on our patents, worked on this technology, and continued to push the frontiers of where lithium iron phosphate battery chemistry and battery solutions could go. Continuing with that theme in 2011 and 2012, we had an opportunity to work with the Department of Defense. And the Department of Defense was not interested in lithium batteries, mostly because of the bad name that lithium cobalt-based chemistry has given to lithium batteries, the potential for thermal runaway and fire. You all may remember that that Samsung phone, I think it was the S7 or the S8, which was banned from flights because of the potential to go into thermal runaway. But the Department of Defense gave us an opportunity, and we wanted to show that really you don't have that issue with lithium iron phosphate chemistry. And so we worked with the Department of Defense for some solutions. And as you know, lithium batteries just can do so much more than what lead acid could be. Lighter, more energy density, huge number of cycles, great cycle life. And so we were able to prove these solutions with the military and have had successful deployments, both in Afghanistan and with the Department of Defense and Iraq as well, but also have offered some products through the military. In 2013 and 2014, we expanded our product line. We continued to work to expand the product line, offering mobile battery bank solutions on wheels for commercial customers, etc. Again, still working with the film industry, but we're really starting to expand our offerings. And lithium iron phosphate batteries were really coming to be the industry standard. In 2015, and we relaunched as SimpliPhi Power. And our goal here is really to provide a broad range of solutions for both commercial and residential battery backup and battery storage systems. We continued to develop more products, and in 2017 through now, we've been growing our product line to offer really plug and play kind of features. What you can see on your screen there is a high voltage system. In addition, we have outdoor rated battery banks that can house inverters as well. And then more recently, as I mentioned, in the end of 2021, Briggs & Stratton purchased us, and we were able to leverage a larger corporation with more resources to come out with the new product line, a couple of new batteries, and we've come out with our own inverter, which I'll be telling you briefly about later on. Okay, so let's talk just briefly, and the topic of this training is not really on battery chemistry, although I'm producing a training for battery chemistry that you might be interested in. And if you are, keep checking back on the website. I'll be delivering that training at RE+. But there are a number of different types of lithium batteries, right? There are lithium cobalt oxides, there are lithium nickel manganese oxides, lithium manganese oxide, lithium iron phosphate is the one that we employ, and I'll tell you why. And then there's the nickel cobalt aluminum oxide. Basically, this is the cathode. This is the side of the battery which attracts the lithium ions to it. And so batteries work basically by having two different locations for lithium ions to be. One place is more favorable than the other. So the metal oxide is what we call the cathode. That's the side, that's the positive side of the battery, and it's a site where the lithium prefers to be. It's more energetically stable. The other side of the battery, the anode, is typically a graphite network, and the lithium can be stored in the graphite network as well. And so when you charge a battery up, the lithium goes over to the anode side. When you discharge it, the lithium is attracted to the cathode side, the metal oxide side. And the two sides are separated by a semi-permeable membrane, a membrane that only allows lithium through. And so the electrons have to travel a different direction. And so that's how we run those electrons through the load. When a lithium ion moves to the cathode, it draws an electron from the other side of the battery over to the top positive terminal. And that's how we run our loads. So why lithium iron phosphate? So some of the other lithium chemistries are actually a little bit more energy dense. You can get more energy at a slightly less weight with the lithium cobalt chemistries. The problem with that, right, is that they're more dangerous. They're more prone to thermal runaway, and they're more prone to fire. There is a need for them, right? So in extremely lightweight, high power demands, the lithium cobalt oxide is a good chemistry. For instance, the helicopter that NASA recently flew on Mars, or a high performance car, right? You would want a lightweight, really energy dense battery, but in that circumstance, right, you're more prone to problems, you're more prone to fires. So lithium iron phosphate delivers a much greater cycle life. So these batteries are rated at 10,000 plus cycles if you're careful in the way you discharge them. And if you're charging and discharging, cycling your battery once a day, that's 27.4 years, right? So you can get a lot of lifetime out of lithium iron phosphate. It's really one of the best chemistries, if not the best chemistry for cycle life. Hard to compare. What is form factor? So form factor is the type of cells that are used to make the battery up. We only use a cylindrical form factor, and that means we have cells you can think of like AA, AAA cells, cells like that. And the reason is that a cylinder is very easy to keep in a rigid shape. In terms of pouch cells, so pouch cells you might be familiar with in phones. I've put this picture of, that's a Apple pouch cell that I took out of an old iPhone. I had changed the battery in an old iPhone, and I had that pouch cell around me. But you might notice that pouch cell is swollen. It bubbled, which actually had pressed the iPhone apart. Now, this was an older iPhone, I think maybe an iPhone 4 or iPhone 5. But that can happen to pouch cells. They're just not as durable, right? You want your home batteries to last for many years. A prismatic cell is also a rigid type of cell, where you have the casing be rigid, but the energy density in the prismatic cells is not nearly as much. So we only use cylindrical form factor, and that allows us to offer one of the best warranties in the industry. Okay, so let's talk about our product line briefly. And one of the things about our product line here at SimpliPhi is that we want our products to be scalable. So when you're looking at our batteries, when you're looking at our inverters, I want you to think of those as building blocks, right? So you might, if you're starting off with a 3.8 kilowatt hour battery, right, and you're trying to hit, let's say, 8 kilowatts, you can use 3 of these batteries to more closely hit that 8 kilowatts than you could if we just offered a 15 kilowatt hour battery, right, or very large solution. So these batteries can be paralleled, give you pretty close to exact matches for people's needs. Okay, so our most common battery that's out there in the field, there are thousands and thousands of these batteries out in the field in many different countries around the world, is our Phi Battery. And the Phi Battery is 3.8 kilowatt hours of energy. Right, that means that if you discharge this over 2 hours, you'd be getting about 2 kilowatts per hour out of this battery, 1.9. Now, the capacity of a battery is the amount of energy that it holds. It holds 151 amp hours. That means you shouldn't do this, but if you were just to discharge the 24 volt battery right? In 1 hour, you'd have 151 amps. Now you can't do that because we'll talk about how quickly you can charge and discharge batteries, but that's a capacity, and energy times it, power times the time gives you an energy. So capacities for batteries are often specified either in kilowatt hours, power times time gives you energy, or they're specified in the number of amps, the number of amp hours that the battery has, but then you have to keep in mind what the voltage is. So our Phi battery comes in 2 different voltages, 24 volt or 48 volt. 24 volt and 48 volt batteries both have the same number of cells. It's just they're arranged a little differently on the inside. And so for a 24 volt battery, you have 8 stacks of cells, right? But there's a larger number of cells. I think it's about 20 cells in 40 cells in parallel on a 24 volt one. So you get 151 amp hours out of that, but it's only at 24 volts. The more common battery is our 48 volt battery, and you get 75 amp hours out of that battery. And so these batteries, of course, that's the capacity of a single battery. If you want to build a large battery bank offering maybe 20 kilowatt hours of battery storage, you could do that. These batteries never should be connected in series, only in parallel. So you only connect these batteries in parallel. So you choose the voltage you want to be at, the 24 volt or the 48 volt. And then let's suppose we had 10 of these 48 volt batteries. If you have 10 of those batteries in series, then you'd have 750 amp hours at 48 volts, or equivalently 38 kilowatt hours of energy. These are modular and scalable. The more you put in parallel, the more capacity you have. Okay, these are also designed to be drop-in replacements for lead acid. So as many of you probably have dealt with in the past, if you haven't had this unfortunate experience, lead acid batteries just don't last. Even under the best conditions, lead acid batteries are going to die somewhere around 5 to 6 years in. And unfortunately, they'll often die much sooner than that. So if you have customers that have existing solar installations and they have battery backup and they have a lead acid battery in there, these batteries are designed for you to be able to just replace that battery bank. The nice thing about lithium iron phosphate batteries as well is you get a lot more range in how much of the battery you can use, right? Even the deep cycle lead acid batteries, they're really telling you to only use about half of the energy that's in the battery because you don't want to cycle it too deeply, otherwise you damage the battery. Lithium iron phosphate batteries, you can cycle them all the way to 100% depth of discharge. Now you might want to limit that a little bit for longer longevity, but these batteries are made and basically the chemistry makes them more stable under larger depth of discharge situations. Okay, we also have a smaller 1.4 kilowatt hour battery that's lighter, it's 33 pound, it's better for mobile applications. The specifications are listed there. It also comes in a 12 volt version at 115 amp hours and a 24 volt in 57 amp hours. So it's about 1/3 the size of the bigger batteries. It does have an integrated battery management system, and there's a breaker on all of our batteries for you to be able to turn them on and off easily. We also offer a product line called our access cabinets, and our access cabinets are outdoor rated cabinets that contain both a battery and one of the industry leading inverters. So here you can see a battery bank of 6 of the Phi batteries. That gives you 23 kilowatt hours of storage paired with a solar inverter. We have other inverters available as well. And this thing, the beauty of this is really it's plug and play. You can install this outdoors or indoors. About the only thing you need to do is make the final electrical connections here to the system, put in your disconnect switch and hook it up. So if you're looking for fast, quick installations to be in and out of the customer's house and move on to the next job, those access cabinets are a good option. Our newer line of batteries are offering communications, and batteries and home energy systems are really moving this direction. In fact, almost everything is moving in this direction. Washer and dryers are now Internet of Things ready. You're able to monitor your washing load from away. Now, why would you want to do this with a battery? Well, there's a great advantage of having communication systems with your battery. Your battery can communicate with the inverter. It can communicate with the charge controller. It can tell it how much state of charge is left. It can tell it how many batteries are in the bank. And so there's a huge advantage for offering this to your customers, right? They'll know a lot more about their system. It can store history. It can store fault codes, etc. It's a little heavier than the Phi battery. It's the same capacity, 3.85 kilowatt hours, I think is the actual spec. Like everything, it's UL certified. And you get a little bit of a higher maximum discharge rate. You can surge this battery at 100 amps because we've got a 120 amp breaker in there. And so this is a choice where many people are moving to a battery that has communications on it, and this is one. It does come at a slightly higher price tag, approximately 20% more, but you're getting a lot more from that, and you can monitor this remotely, unlike the other batteries. Okay, so they are limited, and the limitations in the number of these batteries that you can put in parallel is somewhere around 72 to 75 batteries. That has to do with the Cat5, Cat6 connections. The communication signal, you're going to daisy chain one battery to the next, to the next, to the next, to the inverter. And if you have too long of a chain of batteries, the communication signal gets too weak for the inverters to read, etc. However, 75 batteries, 75 times 3.8 is somewhere 250-ish kilowatt hours of energy storage. It's a very large amount. If you need more than that, you probably are interested in one of our high voltage solutions, which we have. Okay, and then the newest thing that we're introducing, the newest product that we're introducing here, and like I said, I'm trying to move quickly through these products so we can get into the charging and discharging and state of charge science of our batteries. But we are introducing this inverter. It's a 6 kilowatt inverter. Again, think of it as a building block. 6 kilowatt inverter. So each inverter that you put in parallel can offer you 6 kilowatts, 240 volts. It can surge up to 12 kilowatts for a fraction of a second to turn on things like a pump or a heavy compressor or something similar, right, which has a high startup draw. It can surge for a longer period of time at 9 kilowatts. And again, you can put a number of these in parallel. You can put up to 9 inverters in parallel to give you 54 kilowatts of power, 240 volt split phase AC. We don't yet have a 208 volt version, but we plan on offering that soon. Additionally, the batteries that are there are 4.9 kilowatt hour batteries. It's our biggest battery bank. And the reason we sized those at 4.9 is so you can get right up to the 20 kilowatt hour limit for many garage installations. These batteries, you can put up to 72 of these batteries in parallel, offering you 350 kilowatt hours of energy storage, which is huge, right? A typical home uses about 10 kilowatt hours per day if completely disconnected from the grid, right? So these batteries and these inverters are also outdoor rated. You can hang them directly on the wall. The batteries come with a wall plate, and so these are easy to use for outdoor installations. Of course, like all lithium iron phosphate batteries, there are temperature considerations. These batteries cannot be charged in temperatures below freezing. So when the internal temperature of the battery is below freezing, they can't be charged. They can be discharged down to, I think, -4 Fahrenheit. So pretty cold temperatures, 32 is freezing, right? So pretty good cold temperatures they can discharge in. But that's a consideration if you're doing this in extreme cold environments. You might want to install these indoors or in an insulated cabinet, etc. Okay, so we also offer high voltage solutions, but we can leave that for another topic. Let's get into charging characteristics of batteries. Okay, and again, if you have questions as I'm going, please pop them into the chat, the Q&A section. I will get to these questions. I will get to these questions at the end. We'll go through each one of those questions in detail. So charging characteristics. Okay, so we rate our batteries at a charge rate of C/2. And what that means is the capacity of the battery in 2 hours. all right? So if you have a 3.8 kilowatt hour battery that offers 75 amps of charge, that's what our 48 volt Phi battery does, 75 amp hours of storage. If you divide that by 2 hours, then you would get 37.5 amps is the max charging rate. Keep in mind that our 24 volt Phi battery, same with the Amplify, the Amplify and the Phi batteries, the 24 volt Phi battery is 150 amps of capacity. If you discharge that in 2 hours or charge that in 2 hours, you'd be looking at 75 amps. That's the maximum rate, but that's per battery, right? So our most common battery, the 3.8 kilowatt hour, 48 volt battery, it's got 75 amp hours of total charge. Divide that by 2 to charge it up in 2 hours, and the max rate of charge per battery is 37.5 amps. So if you had 10 of these batteries in parallel, right, we only put them in parallel, then you're looking at 375 amps DC at 48 volts, okay? So keep those things in mind. It's a similar calculation for the 1.4, the 24 volts. So a couple of things to say about this. You want to be very careful to size your system properly. You also want to be careful about multiple charging sources running at the same time. Let me give you an example. Let's suppose that you have a solar array, and that solar array is running through a charge controller. Maybe you have 40 amp charge controller, something like that, which is outputting power to the battery. You have to be careful not to have a second charging. Maybe your inverter has AC charging built into it at the same time. These two charging sources could be going, and you want to be careful to either, one, choose an inverter that's got the charge controller built into it, or two, try to have your charge controller, your MPPT, be able to communicate with your inverter. If not, adjust your settings carefully. The battery management system inside all these batteries is really there to balance cells. Yes, it's also there to provide a low battery cutoff point. It's also got a breaker in it, 100 amp breaker, but that's really a surge breaker, right? That surge is that allows you to surge your battery at a rate higher than what is recommended for charging. So you can damage these systems. So be careful to get your charge controllers set up properly. Okay, so the charging characteristics. You want to limit the charge rate on various devices. About every MPPT out there, almost every one that exists now, right, will offer you the ability to control the rate of charging. Inverter chargers are not so good at this. You can set most inverters to limit the charging rate, but I think their settings are a little less reliable. And we'll have problems occasionally after a firmware update where maybe the settings got switched back to a default by accident, and that can damage batteries. So we want to make sure to get things set up properly and be careful with these settings. Okay, the nice thing about the Amplify battery, the battery that's got communications in it, is that battery will tell the inverter how quickly it wants to be charged, how quickly it wants to be discharged, what its state of charge is, etc. These settings are auto-populated right into the inverter. So the Amplify battery is more plug and play, a lot safer of an installation for somebody installing solar, and it offers the additional feature, right, that it has these communications and you can get notifications if you have a problem with your system, instead of waiting for the customer to call you back and say, hey, my batteries aren't working, what's going wrong? Right? This is a battery that can be remotely monitored, as can our new batteries with our new inverter as well, the ones that I presented to you earlier there. Okay, so AC coupled systems have some further requirements. There are electrical regulations about your AC system, how quickly you're allowed to charge, whether you're allowed to charge off the grid or not, depending on what incentives you might have applied for, and local guidelines, etc. So look those up, be aware of the guidelines in your area, as well as follow the NEC US Electrical Code. Let's talk briefly about how a battery charges. Batteries charge with several steps in a cycle. Now, the first part of the step for a battery to get charged, right? So let's suppose we have a battery that's discharged down to about 20% state of charge, and we want to charge it up. Sun comes out, the solar is going, and we start what we call the bulk cycle of charging. Now, if you look at the graph that I've shown you on the screen, it's a little bit small. I guess you can see my mouse. I hope you can see my mouse. But the bulk cycle is done at a constant current. That's what the CC stands for there. Constant current means maybe your charge controller is outputting 40 amps, right? Or 100 amps, right? Depending on your size of your battery bank. It's going to keep charging the battery at that rate, 100 amps coming in, just constantly coming in, right? As that amperage comes into the battery, the voltage of the battery starts to increase. Now, keep in mind, if you're monitoring the voltage of your system while the battery is charging, what you're really looking at is the voltage of the charging system, not really the battery's voltage, but the battery's voltage will start to increase and increase and increase, and eventually the voltage of that charging system, the charging system has to keep increasing the voltage in order to push that charge in at the same rate. So if I want 100 amps when the battery is mostly discharged, it goes into the battery fairly easily. However, once the battery is mostly charged, to put 100 amps into that battery system, right, requires a greater voltage. You can think of the voltage and the current as maybe like a pressure and a flow. So if you had a pipe containing water, the voltage would be like the pressure differential in that pipe. How much pressure is the water under? The current is how much water is flowing. And notice in this bulk phase, that's a constant current process. The current is constant, whereas the voltage is increasing because you need to put more pressure to get more charge into that battery as it fills up. Once the battery reaches a certain voltage, the bulk cycle ends and we start the absorb cycle of the battery. The absorb cycle is really a top-off cycle of the battery. The setting for this on our batteries is 56 volts DC. Once the battery charges up to, once the charger reaches 56 volts DC, then we enter the absorb cycle, and this is a constant voltage, right? So we want to hold the charger at 56 volts, and the duration here is just for 6 minutes, okay? And that should top the battery off pretty close to 100% state of charge. Now, there is an additional cycle for lead acid batteries. There's a float as well. So if you have a renewable energy source, you might want to float your batteries, and that'll just ensure that the batteries stay charged at 100% state of charge. The voltage for that is not listed here, but it's 54 volts for a system. You don't want to float the batteries if you're using something like a grid-tied system because it's kind of a waste of energy. You're not really putting much into the system. And unlike lead-acid batteries, which have a slightly higher self-discharge rate, one of these lithium iron phosphate batteries discharges at something like 1% a month. So you're not really losing energy from self-discharge in the lithium iron phosphate batteries. Okay, additionally, you do not want to use equalization. There's old charge controllers, older systems might have an equalization phase. You want to set that time to 0, and you want to set those volts to 56 just in case the system accidentally goes into an equalization phase. You do not want to use an equalization phase. I think my understanding of that is that was a buildup of sulfur on lead acid batteries, and that equalization phase was used to kind of burn them off and typically be done about once a month. Okay, so what's next on this charging cycle? There's also a rebulk voltage. So the rebulk is going to be the voltage at which, as the battery gets used, once you hit the rebulk phase, that setting, the charge controller will start to charge the battery again. So let's suppose you set the rebulk at 52 volts because you want, you know, to have maintain a high state of charge for kind of battery backup situation. Then the rebulk would be when that battery starts charging again. Okay, so all of these things are changeable, and we have manuals and integration manuals on our websites that you can look at to reference these. I'll also be sending you all a recording of this presentation, so you'll have this as well. Okay, so inverter capability, you want to make sure that your inverter has the ability to have all of these set points programmed into it. And so you'll want to be able to program, when you program your inverter for battery commissioning, You want to make sure that you have your voltage set points properly set so that the battery doesn't overcharge. The time when batteries get damaged is either they are cycled way down too low to 0% state of charge, or they're cycled way too high to 100% state of charge and you've got a high voltage on the battery. So normally that's the time when your battery is most vulnerable. So you don't want to be overcharging these batteries and you don't want to over discharge them. And I'll get into discharging in the second half of this presentation. Okay, so how do you know whether the inverter is capable? I also work on the technical services side here, and I'll get calls coming in saying, hey, I got this inverter. It's maybe this cheaper inverter, which is often happens. I got it, came in from China, and it seemed like it was going to work, but then it doesn't work. Well, what you want to really look for here is, does the manufacturer of the inverter offer a warranty for lithium-ion batteries? Right? If they do, then the system is probably designed well with lithium-ion batteries in mind. Okay, so look for that as you're deciding what kind of an inverter to install, etc. There's also, as these batteries charge and discharge, the BMS can do a shutdown protection, and some systems might require you to come out and restart the batteries manually if the system has gone into a shutdown. And I'll get into that a little bit more. I'll also use the words external charger here. What I mean by an external charger is really a plug-in wall charger. You want to be careful of cheap plug-in wall chargers that are used, especially for like things like e-bikes, etc. You don't want to apply these to the lithium iron phosphates. They run at too high a voltage. Many of the cheap chargers will run at 56 volts. If you have questions on a good wall charger that you can use to maybe top off your batteries in an emergency situation, give us a call and we'll recommend one. Okay, this is the second half of the presentation here. We're going to get into discharge characteristics of batteries. And I'm going to start by showing you what the voltage profile looks like as a battery discharges. Now, keep in mind the scale on the left side of the screen here. We're only varying by about 5 volts, right, over an entire full discharge cycle. The other thing to keep in mind here is that on the left side of the screen, you can see the battery at 100% state of charge start off with 53.2 volts. Okay, I get a lot of questions coming in asking, hey, what voltage will the battery have when it's at 100% state of charge? And the answer is, that depends. It's not a good answer, but that's my answer. And I'm going to explain to you what it depends upon. First, that voltage might be higher. It might be, if you have a resting battery, it might be somewhere around 53.5 volts. The resting state of charge, right, the voltage for that depends slightly on temperature. So as the battery gets hotter, the voltage actually goes up. When a battery gets colder, the voltage actually goes down. That's a small effect, but I'll get into it in a minute. And that's why I can't tell you exactly what it is. Now, this is also a resting voltage. So many of you are probably familiar with solar panels, right? If you test the voltage on a solar panel, when it's in an open circuit configuration, maybe it's high, maybe it's something. I've got the solar panels I have have a large number, 128 cells or high voltage panels. They're at 83 volts open circuit. However, as soon as I start to draw some energy out of those panels, you all know the voltage drops, right? A similar thing happens to a much smaller degree in a battery. And my goal is here to try to explain that to you. So I've modified this presentation a little bit from what my colleagues do, and I'm hoping that I can explain why the state of charge depends on whether or not a battery is in an open circuit condition where no charge is flowing out of the battery versus what the voltage of the battery is when charge is flowing. And I'll show you on the right-hand side of your screen, I've shown you a battery. Now, the battery's got 52.4 volts labeled on it. That's the voltage of the battery itself. But all batteries have a small amount of something called internal resistance. It's what makes a battery heat up, right? It's the resistance of all the wires, the connections inside the cell. It's even related to the flow of the lithium ions inside the cell, right? So that diffusion flow also produces a little bit of heat. So I've labeled that as the internal resistance, little r of the battery here. And this is a diagram we often use in physics classes to kind of explain what's happening in a battery. So the voltage of the battery is 52.4 volts. And if we looked over at our diagram, that would be 50% state of charge, a little over 50% state of charge. However, that's not the voltage that you're monitoring when you're looking at the system. The voltage you see on your system is the voltage on the outside of the battery, right? It's the voltage on the connecting wires. What voltage is that? Well, if a current is flowing out of the battery, so if I have current flowing out of the battery here, so it's going up through the internal resistor, there will be a voltage drop, Ohm's law, right? V equals IR, across the inside of the battery. And so that 52.4 volts, you might lose another volt across that resistor if you have a large amount of current, delta V equals IR, right? So the actual voltage that you get across the wires of your system, across your load, is going to be less than 52.4. That's why people say it's hard, it's complicated to measure the state of charge in a battery. It's not that hard once you understand that simple principle. The other reason it's a little bit hard to measure the state of charge simply from the voltage of a battery is as a battery discharges, that little resistance inside the battery heats up the cells. And as I just said earlier, the voltage of the battery depends slightly on the temperature inside the cells. Okay, but for the most part, the temperature of the cells doesn't change much after they're discharging. And so what I've shown you here is the state of charge, the voltage for state of charge, as a function of the discharge rate. So let me go back up to the previous slide. So as I vary the current out of the battery, right? So a C/2 discharge rate, that's the lowest curve that's here, that's discharging our battery as fast as we can, right? So in the case of our Phi 48-volt battery, that would be 37.5 amps coming out of the battery. You can see that even at 100% state of charge, or close to 100% state of charge, right, we're down at 52 volts if we're discharging with I being 37.5 amps. If we slow the discharge rate down, let me go back to my figure. If I slow down the discharge rate, then that means I is smaller and the voltage drop across the internal resistor is smaller. That means that the voltage that we measure on the outside of the batteries, the connecting wires, right, is going to be a higher value. And so you see that there's a significant difference between discharging at 37.5 amps, right, and 25, which is a C/3 discharge rate. So 25 amps at 50% state of charge, right, you're about 0.3 of a volt higher, right? And if you discharge at C/5, which would, I think, be, I can't do that math in my head very quickly, but I think it would be around around 15 amps, then, right, then you're going to have much closer to what that voltage profile looked like for a resting battery. So notice that this graph is titled Discharging Under a Load, and the other one was titled Discharging with an Open Circuit. So if you started to discharge your battery a little bit and then opened the switch and measured the voltage each time, the voltage across the battery when no current is flowing would just be the voltage of the battery. Okay, so this is open circuit versus under load. And that's why battery monitors have a little bit of a challenge in terms of estimating the state of charge. And that's a common question that we get. Why is a state of charge, so hard to keep track of? Okay, I don't want to belabor this, but this is also a discharging, and I'm sorry I don't have the reference on there for you. I thought I had typed it in, but this is a discharging lithium iron phosphate battery, and it's discharging at different temperatures. So you can see that when the temperature is 40 Celsius, you're getting the most voltage out of the battery. And then if you discharge at really cold temperatures, you shouldn't, but if you discharge at really cold temperatures, that voltage drastically changes by, let's like 15, 20% there. Okay, so I don't want to harp on that because most batteries are kept at a kind of constant temperature as they're discharging, but there is some function of temperature in the state of charge calculations. Okay, 5 discharging characteristics. So our batteries, again, just like the charging rate, we recommend that you discharge these batteries. The max limit is C/2. So This really shouldn't be as big of a consideration in the discharging rate. And the reason I say that is most customers are not going to want to have their battery bank discharge in 2 hours, right? So most customers are not going to, size a system to only have 2 hours of battery backup. Most people are going to want something more like 10 hours of battery backup. But the max discharge rate is similar to the max charging rate for these batteries. It's C/2, which is 37.5 for our 48-volt battery, double that for the 24-volt battery, etc. Okay, and then in terms of state of charge, I mean, I've given you the profile for what it looks like for a 48-volt battery. If you want to know what it looks like for a 24-volt battery, you're just cutting those voltages in half, etc. So there are some considerations to make for Amplify batteries as well. I talked about how many of those can be in parallel. As well, you want to make sure that the inverter has the protection for discharge, etc. The Amplify has that kind of built into the battery management system. Okay. So for the Phi Battery discharging characteristics, it's the same kind of thing. These batteries do offer you a surge. So the Amplify will give you 100 amps for a surge for 10 minutes. It's perfectly fine to discharge at this high rate. It's a little bit above C, but for a short amount of time. And the reason is that when you're discharging at a really high rate like this, it produces heat inside the battery cells, right? And if you do that for too long, the battery cells can get hot and then you can start to cause damage. So temperature can damage the cells with time, but they do offer you a surge, 80 amps for 10 minutes. And that's a little bit more than 4 kilowatts of power per battery. If you have multiple batteries, that number multiplies as well. Okay, and then the Amplify battery, as you can see on the bottom, has a 100 amp surge. And the 1.4 kilowatt battery, the smaller one we offer, has 60 amps of surge. Okay, so these batteries should be sized, and we're going to get into sizing a little bit. For residential use, we typically are seeing these in grid-tied backup. You can either have grid-tied, you can even have off-grid with these, of course. And so there are considerations that go into each of those. Of course, for a grid-tied system, you want to make sure that your inverter, well, for both grid-tied and off-grid, you want to make sure that your inverter is not drawing power out of your batteries any faster than this. So you get, for each battery, with not looking at the surge, for each battery under normal conditions, you're getting about 1.9 kilowatt hours from our Phi batteries. So if you have a 6 kilowatt inverter, you're going to want to have 4 batteries to run that 6 kilowatt inverter. Okay, so you can use inline breakers for protection. However, some people will come to us and say, hey, I know my customers aren't going to be drawing, I'm putting in a 12 kilowatt inverter, but I know my customers are not going to be drawing at 12 kilowatts. They're only going to be drawing at 7 kilowatts. And so I want to install just 4 batteries here. And so I can put a battery bank with 4 batteries in. And even though I know these batteries are not capable of a continuous discharge rate at 12 kilowatts, can I just put fuses in, inline breakers in, to prevent the system from drawing any faster than the batteries should? Can you do that? Yes, you definitely cannot rely on our internal breakers, because our internal breakers are sized for a surge. Right? And there's nothing that would make those breakers go off at 37.5 amps per battery, right? They're capable of surging up to 80 or 100 amps. So if you installed inline breakers, the problem with this is that these breakers have a lot of variation in how they respond. So I will get into that a little bit. Again, on the discharging, just going over this, I think we've kind of covered this, but the rate is per battery, right? And this is an example where we're going to do a calculation, but example when an inverter is too large for a battery bank. If you have 2 3.8 kilowatt hour 48 volt batteries, the max discharge rate you can have there is 37.5 amps per battery module. You got 2 of those, that gives you 75 amps. 75 amps at 48 volts, right, is the amount of power you could draw out of your battery bank. if we put in a 60 amp DC breaker, that should prevent the battery bank from discharging faster than 75 amps. I'll get into a little bit about how breakers work here and how slow they can be to respond in a second. So let's talk about that. So would the breaker work? Well, yes, but here is a graph showing you kind of when a breaker will trip. And so this breaker trips at about 125, 115% of the setting. So this is a 60 amp breaker, but you're going to have to put in more like 80 amps to get this thing to trip. And right, the more current you put in, the faster it'll trip. But you can see that at 115%, so somewhere around 70 amps, this thing could take up to 9 minutes to trip, to heat up and trip. And then, you know, this breaker is claiming to trip much faster right at the 100% mark. But unless you exceed the 125% mark, it could also take a longer time, up to 9 or 10 minutes, 500 seconds there in order to trip. So there's a lot of variation in the breakers themselves and in the specifications of the breaker. So just keep that in mind as you're sizing a system. Again, this is a fuse, and this fuse is telling you, okay, at 150% of the rated capacity, which would be 90 amps for this fuse, it's still going to take 10 seconds to trip. Probably wouldn't damage the battery if you had that in and you had the fuse sized properly. But these are considerations to make if you're going to put breakers, DC breakers and fuses into your system. Okay, the last thing I want to mention here on the discharge cycle is what we call the knee. And when a battery is discharging quickly or towards the end of its life, right, the battery can drop off. And after we hit about 10% state of charge, if you're discharging quickly, you can very rapidly hit this location where on the graph the voltage drops. So on the vertical axis we have a voltage, and on the horizontal axis we have time, and you can see there's this rapid drop off. And if you hit that, you can trip the battery's low voltage, low battery connection. And so you hit this low battery disconnect, and so the low battery cutoff will hit. And so if you're sneaking up on it, if you're discharging very slowly, then the battery management system will likely catch that, and you won't have the battery management system trip. Sometimes if a battery is run all the way down very slowly, the system will catch it. But if you do it really quickly, sometimes the battery will need to be reset. And the way you do that is you just flip the breaker off and on the battery. Okay. I want to pause briefly, give people a chance to kind of maybe catch your breath. I'll take a sip of water here. If you have questions, feel free to drop them into the question and answer. And then I'm going to jump into the state of charge, and we're nearing completion here. So again, I appreciate your attendance, and I appreciate your attention as well. We're going to talk briefly about state of charge. I've already been mentioning it with our graphs, but let's go ahead and jump into the last section of this training. Okay, so as I mentioned, there's a resting state of charge and there's a state of charge under draw. So when we say resting state of charge, we mean that the battery is not charging up, nor is it discharging and powering loads. You could have a load connected, but the battery is not running that load at the time. Okay, and then there's also the kind of state of charge consideration where we have to worry about, okay, how much current's flowing out of the battery? How does that affect the voltage for the state of charge? And then there's kind of the real world expectations versus controlled testing voltage points. And so what we want to look at is we want to look at the state of charge, and we want to understand that graph. And as I was trying to tell you, it really depends, the voltage of the battery when it's at 50% state of charge really depends on whether you're drawing current out of the battery or not. Okay, and so what we also recommend is that some systems, some inverters especially, are very bad at monitoring the state of charge of batteries, and so we recommend that you get a battery monitor. I think the Victron 712 is a great monitor that we recommend that seems to do really well with lithium iron phosphate batteries. Okay, as mentioned before, this is the state of charge, right, for a battery. This is a graph of the state of charge for a battery under load, right? And so when the battery is discharging at a rate of C/2, you have a lower voltage even for the same state of charge. So if you're at 51 volts, but you're discharging rapidly, you still could be at 70% state of charge. So if I can put my mouse there, you're a little under 70% state of charge, but you're discharging at a very high rate, right? But if you're at 51 volts, you also might have 80% state of charge, or even 85% state of charge, 83, something like that, depending on how quickly the battery is being drawn. So this is the state of charge for a discharging battery. Okay, so most charge controllers have some advanced programming for charging and discharging, and so the settings that we're going to be putting in here are the settings that tell the inverter when to, hey, stop discharging the battery, stop selling the energy to grid, and start charging that battery up again. That's the rebulk recharge setting in the inverter. If you set that around 51.2 volts to 52.8 volts, then you're looking at keeping your battery more charged. If I go back to the previous example, if we're setting this around 51 volts, sorry, I just realized I'm making the mistake of, this is the percent the battery is discharged here on this curve. So I apologize for that. But looking here, if we're at 51.2 to 52.8 volts, and we look here, try to determine what the state of charge is there. So 51.2 volts, well, if you're drawing, right, you might be 65% discharged, which means you've got, maybe 35% of the energy left in the battery. But if you're drawing at a slower rate, right, at 51.2 volts, you could be 85% discharged. Okay, and so keep that in mind as you're looking at the voltage. It depends on how quickly you're discharging the battery. Okay, so you can have the generators come in. You can have a set point on a generator come in and say, hey, when the battery drops down to 20% state of charge remaining, right? So 80% discharged, kick the generator on. So that can either support your loads, or it could also charge up your battery as well. And so some customers will want to sell their energy back to the grid as well. Some customers are going to want to kind of keep that battery topped off for emergency situations. And so have that conversation with your customers there. So we've neared the end of the content of the slides that I've prepared, but I'm happy to go into the question and answer phase, and I'll try to answer any of the questions I have. And if I don't know the answer, then I'll get back to you with that. However, if you are on here for the NABCEP credits, I want to tell you to stay on till the end. I'm going to ask you to email me, and I will send you those NABCEP credits. Additionally, I want to tell many of you are maybe part of our Elite IQ installer program, and so we have a qualification program where we certify different installers and put them on our map. The great thing about this program is you're going to appear on this map if you join this program, but I've got to tell you a couple of incentives for you to join. So one, if you join this program, we have a feature in our IQ newsletter, which talks about new installers which have joined the program. Again, you're added to our map. This IQ newsletter goes out to thousands of people, so several thousand people read this, and really the most popular section is on a featured article in the newsletter about a new installer. Additionally, like I said, you're on our map of somebody where to buy our batteries and where to install our batteries. But maybe this is the best one. We offer cash back to you. And so there are two ways you can get that. One, if we choose one of your photos to win our photo contest, our monthly photo contest, you'll get a $250 credit towards batteries. But the bigger one here, and our CEO just approved this cashback program for the rest of the year and possibly indefinitely is that per battery you install, we will send you a $25 check once you register that battery, okay, per battery. So if you put a 10 battery bank in, we will send you a check for $250. If you install 100 batteries in a year, we will send you a check for $2,500. So this is a pretty good incentive if you're installing a decent number of our batteries, and it's pretty easy to work through. And so what am I looking for here in these photos? We really want to see photos with people in it. I mean, a great installation like the one in the bottom right-hand corner, it's nice to see pictures of that. We love to see those pictures. But additionally, you know, seeing pictures where people are in front of the systems that you've installed for them, or you, the installer, are in front of the system you're installing. We love seeing these pictures, and these are the kind of pictures that often win our photo contests. And so we also roll entries. So if we have a number of good entries for a month, we might say, hey, you didn't win this month, but we're rolling your entry over into the next month. And so I encourage you to send us pictures as you're doing these installs. There are rewards associated with it. And like I said, the IQ installers, those in our IQ program, are eligible for $25 per battery they install. And over the course of a year, that can really add up. So if you want to join this program, you can either pass a test, and that test is available on bluevolt.com. Send me an email after the talk. I'll tell you how to do that. And the other way to join the program is to simply follow this link that's on the screen here. But if you just go to our website, if you look at our website, we've got a lot of good information here. So it talks about our IQ installer program on the website. Additionally, I want to point out, so the IQ installer program is here. We highlight trainings. We have a training calendar here. We have how-to videos. So if you're just looking for something simple like, hey, how do I parallel these 6 different batteries? Do I need to use a bus bar? What can you recommend? Check out this section of our website. The other section of our website I really want to highlight for installers here is these installation manuals and integration guides. So we often get calls from Solarc, from Outback, because we have a very quick customer service. You don't go on hold with us. You call our customer service, we'll be there on the phone to answer your questions and to help you out, and we'll even help you out with settings in other people's equipment. Okay, so there's specification sheets, there's integration guides, which an integration guide is a guide telling you how to use our battery with somebody else's equipment. So many of those questions you might have can be answered in this product documentation section. And then if you're looking for just help sizing a system, we have sizing calculators, and we're working on enhancing those sizing calculators as well. And then spec sheets, etc., for all of our products are here. So thank you for taking the time to look at this. I think I've lost my mouse, so I'm having trouble clicking on the next slide. Maybe the battery has died. Let me see if I can do it with a touchpad. There we go. All right, so thank you. I appreciate it. My email is on here, so training@SimpliPhi Power. I can answer a lot of questions. So let's jump into the question and answer section here. I'm going to read some of these questions off of here and we can go through them. As I said, I might not have the answer to all of them, but is it reasonable to test individual batteries for the health of each one after a battery bank has been operating? Yes, it is. You can test the batteries for, you can test the battery's voltage. And one of the things we recommend when people are having an issue with a battery bank is to disconnect the batteries and test each one of their voltages individually, right? So if you have a battery that you're suspecting there's a problem with it, you can test it individually. Additionally, these batteries are really pretty good, and often if a battery is having problems, often there was a setting which has caused that battery to have problems. So do give us a call, and our technical support can kind of help walk you through troubleshooting of individual batteries as well. Somebody asked, what has happened to the saltwater battery? I had an interesting slide on here. I had a trivia slide on here. So I'm not sure exactly, I don't know much about the saltwater battery. Certainly it's not one of ours. But I had a question for all of you. I'm a physicist, I can't help it. I had put a slide in here and I guess maybe I took it out at the last minute, but to ask you, how is the majority of the energy stored for the grid in the US? You guys think? So 93%, according to the Department of Energy, 93% of grid energy storage is elevated water, right? That's our hydroelectric dams, that's elevated water. And it is possible to pump water back uphill and downhill at about a 90% efficiency, which is pretty close to batteries. So if we want energy security as a nation, why don't we just build more dams? The answer is because most of the easy places to put dams, right, have already been taken, right? There are certain, you need certain geographical features. You need a valley with large capacity to, hold lots of water. And so what's growing really rapidly is battery energy storage. And there's also obviously a real diversity in terms of storing energy. It's much more versatile when individual households have that. Okay, so next question. What problems may arise if the battery bank voltage at the completion of the charge cycle is 2 to 3/10 of a volt less than 28 volts for a 24-volt system? There should be no problem with the charging cycle, right? If it's just a little bit below that, it just means that you're not quite getting to 100% state of charge, or it could also mean, right, that your battery is not, that your charging cycle is not entirely complete. So I don't see that there's a particular problem with that. Maybe you can elaborate and I'll get to it again. What applications would you choose a 24-volt battery versus a 48-volt battery for? What is the essential difference? I guess the essential difference here is just you would choose a 24-volt battery based on other systems that you would need to draw. So if you're running systems that operate off DC, for instance, back in 2019, I did an installation in Ghana. We used 24-volt battery bank. We were in a very remote off-grid location, and we chose a 24-volt battery bank because we were operating 24-volt DC refrigeration systems. This was a remote ice making facility for fishermen. And so that's, generally the choice of when to use 24-volt is really, or 48-volt, depends on kind of what you're running off of it. And if you're running DC stuff off your battery bank, then you might choose a 24 versus a 48. For most home backup, the standard really is 48 now. Why is the C/20 Amplify value used, or C/2, I think, Amplify value used when comparing C/20 used when comparing lead acid batteries, but not LFP batteries? I don't know the answer to that. Lead acid batteries have, there's a large variation in the kinds of lead acid batteries that are used, right? So deep cycle lead acid batteries typically cycle a lot slower than LFP batteries do. But of course, some lead acid batteries are made to have a huge amount of surface area, right? So you could discharge at 600 amps, cold cranking amps for your car. And it really depends on the design of the battery. I think the C/20 amp hour value is probably because when you look at the energy output of a battery, if you discharge it slowly, like a C/20 value, you're producing the least amount of heat inside the battery, right? And you're getting the most amount of energy out. I would say that you wouldn't want to use that comparison for lithium batteries because you can really cycle a lithium battery a lot faster without generating as much loss as you would with a lead acid. So that's my guess there, Fernando. I appreciate that question. Hopefully I did it justice. You just said connect 10, 48. Oh boy, Glenn, I appreciate that. It seems like you caught me saying connect batteries in series. Thank you. Never connect the batteries in series, always in parallel. So it sounds like I misspoke early on in the conversation. So thank you. Sorry, I didn't catch that earlier. Can you scale the Access Phi beyond the 23 kilowatt hours? The answer is no. We can only fit the Access Phi, we can only fit 6 batteries in that system. However, what you can do is you can get a separate battery bank and add 12 more batteries there for another 45.6 kilowatt hours of storage. So you certainly can expand the cabinet, but what you can add an extra cabinet, which can expand your battery bank and still run the same inverter inside. Wow, so I'm reading, our home in Ridgecrest uses 58 kilowatts a day using AC. I'm guessing that you mean in energy use, because you're talking about per day, so 20 kilowatt hours per day. This week it will be over 100 to 110 degrees, but we typically use about 10 kilowatts in the winter, as you noted. Yeah, certainly air conditioners are a huge hit for AC, right? And what you can do by having a battery backup system and an inverter on your house is you can reduce that peak rate that you're being billed at by having your inverter provide some of the energy for your air conditioners in a grid connected system. Okay, given that building codes are driving batteries outdoors and that the high cost of insulating or heating is a problem, how will you get batteries, 60 kilowatt hours batteries back indoors? With this question, I don't know. You know, I don't know what building codes are trending to, other than I'm hearing that garage installations are limited at about 20 kilowatt hours here in California. So I don't know the answer to that. Happy to look into it if you want to send me an email. Appreciate the question. Elliot writes, what kind of design advice can you give if we need help to set up a job? So we have sales application engineers who can definitely help you with sizing, etc. And so I would encourage you to contact our sales application engineers to help you get set up. Is there a minimum charge rate for the 3.8 kilowatt battery model? No, there's no minimum charge rate. You can charge it slowly, you can charge it quickly. There's no minimum. Does the Phi Amplify BMS protect against freezing temperatures? Great question. The Phi battery does not. The Amplify does. So the Amplify BMS monitors temperature and prevents you from charging that battery when it's below freezing. The Amplify BMS also will allow you to discharge all the way down to -4 Fahrenheit. The Phi battery does not, and therefore you want to be careful where you locate the Phi battery. People use, we have blankets, electric blankets or heating pads that we recommend that can be used inside battery boxes, etc. But there's another training on environmental considerations for battery installations that I would recommend you look at. So Elliot writes, will you be offering any webinars on programming and getting familiar with the communications and other software associated with your products? Absolutely, Elliot. So we will be offering another training. So I don't know if you're going to be at RE Plus, the conference out here in California, but we're going to be offering trainings in a couple of weeks at that conference about communications. We have videos online. So if you go back to the website where we were earlier, you can see the videos that we offer about programming. As well as we have integration guides for programming our systems with other people's products. And so yes, there are a lot of trainings online. We'll be offering more of them in terms of our new products as well, our new inverter, etc. So thank you for that question. Tim writes, is it possible to get access to this PowerPoint or a recording after this call? I would like to cover some of this stuff with our sales and design team. Absolutely, Tim. It takes a little while for Zoom to process the recording, but once they do, I'm going to send all of you a copy of it so that you can share it with your colleagues. I appreciate that you found it helpful. I've been using 1 minute for absorb. Okay, so you're only using 1 minute. We're only really recommending 6 minutes at 56 volts. Sometimes people will want to increase the absorb time, but just decrease the voltage. And so, you know, if you want to offer a slightly larger absorb time to make sure you're hitting that 100%, you can, but we recommend that you reduce the voltage a little bit. The absorb feature there is really kind of like topping off the battery, going from that 90 to 100%. So when a battery is charging, it charges very quickly in the beginning, but then we want to slow down that charge as we are topping it off. And that's why often your phone will charge up to 90% really quickly, and then it slows down and getting that last 10%. How does a grid-tied battery backup system with Phi batteries, which doesn't cycle often, if at all, affect the lifetime of the battery? That's a great question, and I'm kind of sorry that I didn't mention this during the talk. So if you cycle the batteries, as I said earlier in the talk, the time when your batteries are kind of receiving the most amount of abuse, I guess I can say, is when the batteries are closest to 100% state of charge or at the lowest depth of charge, so that when you're at a state of charge of like below 20%. So we recommend 80% depth of discharge for something that cycles very often, but you're asking here about something that doesn't cycle very often. And it's completely fine to cycle them down 100% if you're not doing it very often. If low battery restart is 48.8 volts and the low battery cutoff is 48 volts and the rebulk is 48 volts, will this function properly? No, you want to have that rebulk a little bit higher, right? So it won't go back into a charging cycle if it doesn't hit that rebulk voltage. So you want to set that rebulk voltage up a little bit higher, right? Does the BMS have a record of history? It does. In the Amplify system, it communicates that history to the inverter that it's connected to, etc. The Phi batteries does not have a record of history. I want to make sure I'm correct on that, but I think the Phi batteries doesn't remember history. To avoid any battery resets with the customer, what minimum LOC would you set the cutoff to be? We recommend that you set it at a number slightly above 48 volts. You can discharge all the way down to 48 volts without disrupting or harming the battery. But I would say that, I guess, if you set that rebulk and keep that battery at 20% state of charge or higher, right, then you're rebulking the battery once it hits, I think, 50.2 volts is what we recommend. I have a hybrid off-grid system with solar and wind turbines backed up with an AC generator. When excess renewable energy is available, I'm using diversion controllers to primarily limit charge to the battery array, secondary power to a water heater, and lastly, to dump load. I'm sure I need to set the diverters to the max of 56 volts DC or lower, but are there any other special considerations for this design? Edward, that's a great question that I don't know the answer to, and so I'm going to encourage you to call our sales application engineers or our technical support and run through the system with them, and they can help you answer that. I'm sorry, I don't know. Elliot writes, do you have any texts you'd recommend if we go into some of this material deeper or use for reference for sizing, etc.? Certainly, I recommend that you read our manuals and read our information that's on our website. I don't have any good texts. I know my colleagues do. And so if you send an email to training@SimpliPhi Power, we'll get back to you with recommendations on that. I know my colleague Daniel has really great knowledge of texts that are out there. I just don't know any off the top of my head. I'm sorry. Is it able to support 1C charge for short periods of time? Yeah, Hector, you were asking about the surge rate. Yes, we can go slightly above 1C, but only for 10 minutes. So we can surge for 10 minutes, and that's to, maybe you're running something really heavy like a well pump, or using a lot of energy pretty quickly, but only for a short period of time. Yes, you can surge the batteries up to 100 amps for the Amplify, 80 amps for the Phi batteries. Do I have any examples of single line diagrams we could get access to for the Access Phi or the Solarc systems? Tim, I don't know. I suspect that we do. And I would encourage you again to ask our sales application engineers for those drawings. Sorry, I don't know for sure if we have single lines available for you. Elliot writes, I'm eager to join the IQ Elite Installer Program. I've completed the online training and sent certificates in. What's the next step? So if you sent the certificates in, we will contact you back. So make sure you've emailed training@simpliphipower.com, and we will email back to you. We're a little short-staffed right now. We've got a lot of trainings going on, and we've been traveling around the country. My colleague Daniel's in Connecticut this week doing a training there. And so we will get back to you. And so wait for us to contact you, and then we'll get you a pack of swag out, t-shirts, hats, that kind of thing. And then of course you're eligible for our picture program, etc. Kenny, I'm not sure what you mean here by you needing 3-aught. So sorry, I'm not sure I understand the question. Is this webinar available to watch again? Absolutely. And I'm sorry that you got cut off, but yes, I will send it out. I'll send the recording out. Code now disallows mounting batteries over 1 kilowatt in habitable spaces, bedrooms. Yes, exactly. Can SimpliPhi batteries be installed therein? No. So this is the fire code. And any battery that's over 1 kilowatt has to be installed in a designated area. If you want to mount these batteries inside a home, they have to be in a designated room. I just did a fire safety training last week, and so we have to be careful with that. You can mount them in the garage, of course, and you could mount them in a designated room inside the house, but it cannot be a room that has beds in it. Beds, couches, that kind of thing. So it would have to be like a separate, it would have to be like a utility room. Okay, for the case of long-term storage with respect to lithium polymer, is it best practice to discharge 60 to 70% state of charge? I don't know much about lithium polymer. I'm thinking that most lithium batteries, you can discharge more. If you're talking about lithium iron phosphate, then yeah, really best practice is to discharge down to about 20 or 15%. You'll get the most cycle lives. And we're really talking about 10,000 plus for lithium iron phosphate. For lithium polymer batteries, I'm not quite sure what the best practices are. Okay, I think, no, so the answer, Tim, you asked, you noticed that the batteries are really close together in some of our marketing photos. The batteries do not produce a large heat load like inverters would, right? So if you have inverters close together, then those inverters, typically they're processing huge amounts of energy and have a kind of a higher heat generation. So we do get calls in occasionally about inverters being too close together. But yes, you can mount the batteries close together, and the kind of ambient heat between batteries is not going to be an issue. You don't have to worry about dissipation like we do with the inverters. Consider an off-grid PV system with AGM batteries that do not charge fully in winter because there's not enough hours of daylight for float/trickle charge to complete. Would lithium iron phosphate perform better? I think the answer to that is probably not, right? So I've noticed on some installations that I've done locally that the amount of energy you get in wintertime is about 30% of that that you get in the summertime, right? So you get the sun is coming in at a lower angle, you have less sunlight hours, the days are shorter, right? And the farther north you go, the worse this gets. If you're near the equator or if you're in the south, it's not as much of a variation. But if you have an off-grid installation, it's not charging fully in winter, it's really a matter of adding more solar panels to the system. I'd love to tell you to add more of our batteries to get you to buy more, but I think what you really want to do is install a little bit more PV for the winter, or to help offset this kind of discrepancy between winter and summer. The farther south you orient your solar panels, the less of an effect the angle of the sun has, right? And so typically they tell you to angle your panels south at the latitude that you are, which would give you 90 degrees in kind of when the sun is at the equator. so kind of in between solstices. But if you want to offset and get a little bit better production in the winter time, you can angle your panels south a bit more than your latitude, and you'll get a little better performance in the winter, although your performance in the summer will drop a little bit. And the last question here, and thank you guys, I mean, still have over 50 participants in the room here through all these questions. Follow up, if the battery is held at 99 to 100% state of charge constantly, does it affect its life? It depends on the voltage that the battery is held at. So yes, holding a battery at too high of a voltage, if you're floating the battery at 54.5 volts continuously, it's bad. So I would say that if you're going to hold the battery at 99 to 100% state of charge, don't float it at any voltage above what the voltage of the battery would be, which would be around 53.5 volts. But no, if you're not overcharging the battery, if you're not keeping the voltage too high, you don't want to float it at 55, 56, then the battery life shouldn't be affected by holding it high. I should probably follow up on that one because I'm not 100% sure there. So one more time, for all of you that are looking for NABCEP credits, email us at training@SimpliPhi. Because there are a large number of participants, it sometimes takes me up to 3 days to get those back. But I will get those credits back to you. Get an hour and a half for the training today. I appreciate your time. I appreciate all these great questions, and hopefully you've learned something. I'll be sending the recording to everyone in the next coming couple of days. So thank you again for your attention and time. Hope you use SimpliPhi products in the future. And again, remember to consider our IQ program. We can really get you some good reimbursements back. Install 100 batteries, get $2,500 check from us. So thanks a lot. Bye.